Okay guys, next we have a very important theorem, the spectrum. The spectrum of a bundle linear operator on X, Banach space X, is denoted by sigma t and is defined to be the set of all scalars like lambda such that t minus lambda I as an operator here, okay, is not invertible. Remember this lambda, this I is the identity operator. So t minus lambda I is not invertible. When you say this is not invertible, okay, so it means one of these two cases at least happens, okay. So it means when t minus lambda I is not invertible, so we have, this is equivalent to saying that t minus lambda I is not surjective, which means the range of t minus lambda I is not equal to x, or t minus lambda I is not one-to-one. And this is equivalent to saying that the kernel of t minus lambda I is non-zero, has non-zero element. If the second case happens, okay, this lambda is called an eigenvalue of t. So it means in this case, this kernel has non-zero element. So it means there is a non-zero element such that, like x, such that t minus lambda I at x, t minus lambda I at x equals 0. This is equivalent to saying that tx equals lambda x. And this x, this non-zero x, this non-zero element or non-zero vector is called an eigenvector corresponding to lambda. Okay, now look at next. Okay, now when we are talking about the spectrum of operators on a spectrum of bundle linear operators, we have to consider two cases separately: finite dimensional spaces and infinite dimensional spaces. So let's first talk about the spectrum of bundle linear operators on finite dimensional space. To understand this better, I prepare a note for you. Look at this. Let's say, okay, we said x, but here I denoted by h. It doesn't matter, and I will tell you why. Let's say h here is a finite dimensional, let's say n-dimensional Banach spaces. Okay, we can prove that h is nothing but Cn. So it means every n-dimensional Banach spaces, every n-dimensional Banach space is actually Cn. So it means actually it's n-dimensional complex Hilbert space. That's why I choose the notation h. So when we say b of h, which is equal to b of Cn, it means the bundle linear operators on Cn, this is actually equal to this set. What is this set MNC? It means the set of all S squared, or set of all n by n matrices with complex entries. Okay, this means every bundle linear operator on Cn corresponds to a matrix, a square matrix, and every square matrix n by n with complex entries corresponds to a bundle linear operator. Okay, and remember, linear operators on finite dimensional spaces are automatically bounded. Okay, so every operator corresponds to a matrix, and every matrix gives you an operator. For example, look at here. Let's say we have a bundle linear operator on C2, two-dimensional Banach space, or more precisely, two-dimensional complex Hilbert space. T maps x and y, a vector here. You may write this vector as column vector or row vector, it doesn't matter. T maps x and y to 2x minus iy and x plus y. So do you agree with me? This equals actually the product of this matrix to this vector. 2 minus I, 1, 1. Look at here, 2x minus iy, x plus y. So you can see this is a matrix, a square matrix, 2 by 2 matrix with complex entries. This is a complex number, remember. So simply t at xy equals a at xy. Okay. So now look at here. So if T is a bundle linear operator on a finite dimensional space H, something like this, like Cn, when you say finite dimensional. Then when you say the spectrum of T, it means the set of all scalars such that T minus lambda I, remember here, T minus lambda I is not invertible. So, and this is equivalent to saying that the kernel of T minus lambda I is not 0, or the range of T minus lambda I is not equal to H. But in finite dimensional spaces, these two statements are equivalent. These two statements are equivalent. It means case 1 and 2 are equivalent. Okay? So when you are talking about the spectrum of T on a finite dimensional space, so the spectrum of T, one more time I repeat, sigma T equals the set of all scalars such that T minus lambda I is not invertible, and that is equivalent to saying that the kernel of T minus lambda I is not 0. It means simply the spectrum becomes this, all scalars such that when you say the kernel is non-zero, it means there is a non-zero element like x in H such that T minus lambda I at x equals 0. And what is this actually? It means the set of eigenvalues. So the spectrum of a bundle linear operator on a finite dimensional space is exactly equal to the set of eigenvalues. Okay. And one more thing, on the lecture note, maybe here I use H, okay, and little bit maybe here is different, but it's the same. You can follow this, okay. In your lecture note, I think here you have H, and here you have TH equals lambda H, but it doesn't matter. There I use H, here I use X. It doesn't matter, okay. It's the same. So the spectrum of T is equals this. It means the spectrum of a bundle linear operator on a finite dimensional space H is precisely equal to set of eigenvalues. Okay, and look at here. Since every matrix corresponds to every operator corresponds to a matrix, so the spectrum of T, it means actually the spectrum of the matrix of T. It means A. A is the matrix of T. And look at here, this equals this. Look at here, this equals this. All scalars such that there is a non-zero vector in H, but H is Cn, right? Such that, look at here, T equals A minus lambda, or T corresponds to A, the matrix of T, minus lambda. The identity operator corresponds to identity matrix. So these two are equal. So it becomes all scalars such that there is a non-zero vector in Cn such that A minus lambda I xn is 0. Okay, and actually look at here, this is a system actually. This is a system consisting of n equations and n variables. So when we say this is equivalent to saying that this system has non-zero solution. Okay, and look at here, this is the matrix of the system. Okay, this is the matrix of system. Actually, this is a system of equations in the matrix form. So when we say it has non-zero solution, it means the matrix A minus lambda I is not invertible. It's not invertible. Okay, because if it is invertible, it has a unique solution, and the solution is 0. So when we say it has non-zero solution, it means this matrix is not invertible. When we say this matrix is not invertible, it is equivalent to saying that the determinant of this matrix is 0. So put it all together. If you have a bundled linear operator, and look at here, before that let me mention, for a matrix, when you say, for matrix A, when you say the set of all scalars such that the determinant of lambda A minus lambda I n equals 0, what does it mean this? Do you remember from linear algebra? This is the set of all eigenvalues of the matrix A. Okay, and this determinant of A minus lambda I n equals 0 is called the characteristic equation. okay, the characteristic equation. So let's put it all together. So simply it means when we have a bundle linear operator on a finite dimensional Banach space, let's say in dimensional, H is nothing but Cn. Okay, so when we are talking about the spectrum of T, the spectrum of T is precisely equal to the set of the eigenvalues of T. And when we say the set of the eigenvalues of T, it means the set of eigenvalues of the matrix of T, like A. And when we say the set of the eigenvalues of the matrix A, it means this. Okay, it means the roots of the characteristic equations. Okay, when we say okay, the determinant of lambda okay, determinant A minus lambda I n equals 0, this is actually it means here we are trying to find the roots of this characteristic equation. So when we say the eigenvalues of A, it means the roots of the characteristic equation. But you have to be very careful. You can see I mentioned this is no longer true for infinite dimensional spaces. It means if you are talking about the spectrums of bundle linear operators on infinite dimensional space, the situation is very different. There, a bundle linear operator may not have an eigenvalue, or the spectrum could be much bigger than the set of eigenvalues. So it's different. That we will talk about it later. Okay, now look at here. We have a simple example. Compute the spectrum of this matrix. When I say matrix, this is a 2 by 2 matrix, right? So this is actually, this matrix actually corresponds to a bundle linear operator on C2. Okay, so when we say compute the spectrum of A, this simply means the set of eigenvalues of A, because A corresponds to a bundle linear operator and on C2, and the spectrum of that T is nothing but the set of the eigenvalues of A. Okay, you can see here quickly I prepared some explanation for you. The rest I leave it to you. Okay, first we have to find the spectrum of A, which means the set of eigenvalues of A. A is corresponding to a bundle linear operator like T on C2. So we have to find the roots of this characteristic equation, right? Determinant of A minus lambda I2, remember here we are talking about two-dimensional space, equals 0. So you can see here A minus lambda I2 is this, right? 2 minus lambda minus I 0 1 minus lambda, and determinant of this equals 0. It means this is our characteristic equation. So you will find two roots, lambda 1 and lambda 2. Okay, lambda 1 is lambda 1 equals 2, lambda 2 equals 1. Okay, so we have two eigenvalues. It means a spectrum contains these two elements, 2 and 1 here. Now we have to find the corresponding eigenvectors. Okay, you can see here. So it means, okay, 2 minus lambda j minus I 0 1 minus lambda j. J is 1 and 2. When j is 1, we are talking about lambda 1. When j is 2, we are talking about lambda 2. So if here j is 1, we will find the eigenvector corresponding to this eigenvalue lambda 1. When j is 2, we will find the eigenvector corresponding to this lambda 2, this eigenvalue. Okay, it means you have to solve this system. I leave it to you. It means when you put lambda 1, solve this system to find the corresponding eigenvectors. Another time you put lambda 2 here, which is 1, and solve this system to find the eigenvector corresponding to lambda 2. This is easy, I leave it to you. So solve this system. And one more point that I would like to mention, if you remember from linear algebra, here you can see we have two eigenvalues which are distinct, and if you remember, it means different from linear algebra. The eigenvectors corresponding to distinct eigenvalues are linearly independent. I just want to remind you this from linear algebra. So go ahead and solve this system to find the corresponding eigenvectors. I leave it to you, this easy. Okay. Okay, let's take a look at the next definition, resolvent set. So T is a bundled linear operator on X. The resolvent set of T is defined to be, what is this? It means the complement of the spectrum, because the spectrum is a subset of complex number, right? So resolvent set, which is denoted by rho of T or rho T, is just defined to be the complement of the spectrum. So resolvent of T is the complement of the spectrum. So it means the set of all scalars such that T minus lambda I is invertible. Look at here how we define resolvent. It's defined to be the complement, okay, the complement of the spectrum. So it means the set of all scalars such that T minus lambda I is invertible. Okay, so it means T minus lambda I is invertible, right? And the inverse of T minus lambda I is denoted by this, right? T minus lambda I inverse. The inverse operator, it means this operator, is called resolvent operator of T and is denoted by R lambda T. Okay, when we say R lambda T and lambda is an element of resolvent set, it means T minus lambda I is invertible, and the inverse, okay, is denoted by this, and you can see R lambda T, it means the resolvent operator of T, which means T minus lambda I inverse, and lambda is an element of the resolvent set. Okay. Why do we give the definition of this resolvent set? Because you can see the resolvent set is defined to be the complement of a spectrum. Sometimes when we are trying to compute or describe the spectrum of some operators, it is better to find the resolvent set. It might be better or easier to find the resolvent set. Then when you find the resolvent set, you take complement, then you can find the spectrum. Okay, this is the advantage, as an advantage. Okay, look at here. Next we have a very important and interesting example about the spectrum of bundled linear operators on infinite dimensional spaces. Now look at here. What is this C of 0 and 1? It means the Banach space of all continuous complex valued functions on this closed interval, right? Let me repeat again. This is the Banach space of all continuous complex valued functions on this closed interval. Okay, this is a Banach space, right? Okay, this is an infinite Banach space. So we have a bundled linear operator like M from this Banach space, let's say X into X, and this operator is a multiplication operator. It's given by multiplication. What does it mean? Look at here, mu. Okay, look at here. If you take an element here, it means a continuous function. So mu, it means mu is here. Mu must be a function here. Mu at every x in this interval is defined to be, look at here, x times u of x. So this is how we define mu. And of course, mu is definitely continuous, right? Because it's the product of two continuous functions, like x and u of x. So we can show that mu, mu is a function here. So I leave it to you to check that actually this this m is a bundle linear operator on this Banach space x. X is C here. X is C of 0 and 1. So I leave it to you to check that M is a bundle linear operator on this Banach space, which is given like this. Now, what we want to do is to describe or compute the spectrum of M. The spectrum of M. Okay. Okay, so let's do it. We want to compute or describe the spectrum of M. I have done it here for you. Let me explain you. Okay, so we want to find the spectrum of M, right? As I mentioned, sometimes it is easier to find the resolvent or to compute the resolvent set, and then maybe like it might be easier to find resolvent set. When you find the resolvent set, then you can take complement to find a spectrum. So it means if we can find resolvent set, then we can find a spectrum. So now look at here. If lambda is an element of the resolvent set, this means M minus lambda I is invertible. And this is equivalent to saying that, look at here, M minus lambda I as a bundled linear operator on this Banach space. Here's the space of continuous function is our Banach space, our X. Okay. So it means there is a bundled linear operator on this Banach space like S such that M minus lambda I times S equals S times M minus lambda I equals I. What is I? Identity operator on this Banach space. It means I belongs to B of X. It means identity operator on this Banach space. It means it maps every function to itself. Now look at here, M minus lambda I S equals I. We are going to use this equation to find S, and then when we find S from this equation, look at here from this equation, we can show that S satisfies the other equation. So this is equivalent to saying that, look at here, here we have the sum of two operators, and here we have the composition. Just like simply for function, we know that the composition of function distributes over sum. So this equals ms minus lambda is, but is equals s. Okay, so we have ms minus lambda s equals I. Here is composition, and the composition and I and s. So you can see here, ms minus lambda is s equals I. And look at here, now what we have, ms minus lambda s is an element here, belongs to B of X, and I also. So it means left and right are two bundled linear operators here. It means left and right are elements of B of X. Okay, when we say these two operators are equal, this means for every element like u, it means for every continuous function here, we have ms minus lambda su must be equal to iu, and iu equals u because it is identity operator. Correct or not? Okay. So now here, look at here, we have an operator. So like here we have f minus g at u. Okay, so do you remember, like for functions we have f minus g at x equals fx minus gx, similar to that. So ms at u minus lambda times lambda s at u, and lambda s at u is defined to be minus lambda su. Okay, so it means the image of this operator on u minus lambda times the image of s on u. This equals u, right? Okay. And look at here we have the composition operator. So this equals m of su minus lambda su must be equals to u. Okay. Let's continue on another page. So look at this. Yes, let me show you one more time. Okay, now in bottom line, what do we have here? Look at here. This is a function here. This is a function here. This is a function here. And m of su is a function here. So lambda, so su is a function here. So lambda su is a function here. So here we have the difference of two functions here. So what you see here, this one is a function here, and u also is a function here. So left and right are two functions here. Here belongs to C, two continuous functions. When you say these two functions are equal, what does it mean? It is equivalent to saying that for every x in closed intervals 0 and 1, the image of this function at x equals the image of u at x. Okay, like this. Now here again we have like, look at here, we have like f minus g at x equals fx minus gx. So this equals m of su at x minus lambda times su at x equals ux. Now look at here, what is the, okay, look at here, su is a function like v. Look at the definition of m. M is multiplication operator. It maps every function to, okay, to another, okay. Like if we have mu at x equals x times ux, it means, okay, here su is a function, okay, m maps this function to another continuous function, and that continuous function maps every x to x times su of x. It means simply m maps every function to product of that function by x. So x times sux minus lambda su at x equals ux. Now look at here, we have su at x, okay, we can factorize x and lambda here. Okay, so x minus lambda at sux equals ux. So now let's divide both sides by x minus lambda. So we have su at x equals 1 over, yes, if we divide both sides by x minus lambda, su at x equals 1 over x minus lambda at ux. Look at here, what is s? S is actually the inverse of m minus lambda I. It maps every function to a function, and that function maps x to 1 over x minus lambda at ux. Now look at here, this s is the inverse of m minus lambda I. So, and this is the equation of s. Look at here, we have 1 over x minus lambda. So if we want s to exist, it means if we want m minus lambda I to be invertible, it means the inverse, which is s, to exist. Look at here, 1 over x minus lambda times u of x. X belongs to this interval, right? Okay, it means lambda cannot belong to this interval. For example, if lambda is 1/2, then if x takes 1/2, then 1/2 minus 1/2 is 0, is not defined. Okay, division by 0 is not defined. So it means s, the inverse of m minus lambda I, exists. Okay, it means m minus lambda I is invertible if and only if lambda is not here. Lambda is not here, because if lambda is here, then s cannot be defined, because division by 0 is not defined. So lambda cannot be here, right? So look at the previous page. It means if lambda is an element of resolvent set, okay, then lambda cannot belong to this interval. So it means the resolvent set is every complex number except elements of this interval. It means resolvent set is this, the complement of this interval, right? Okay. Now, what is the spectrum? When we find the resolvent set, we can find the spectrum easily. A spectrum is the complement of resolvent set. So a spectrum is just the closed interval 0 and 1. And one quick observation, because soon we are going to talk about this. You can see the spectrum of M is the closed interval 0 and 1, which is a compact set in complex number. Okay, so this is the spectrum of M. Okay, look at here. Next we have an exercise for you. Try to think about it in your free time, which is actually a generalization of this example. Okay, It means this example is a special case of this. Look at here, f is a continuous function. So this f induce a bundle linear operator on this Banach space like MF. And this bundle linear operator is a kind of multiplication operator induced by f. It means MF as a bundle linear operator on this Banach space maps every function to a function here. So MFU must be a function here. So how does it act on every x? It maps every x to fxux. You can see MF maps every function to a function here. But what is that function? The product of u by f. So it's a multiplication operator. We want to describe the the spectrum of MF. I leave it to you. Of course, it is an exercise. You can do similar to this example, but I just give you the answer and quickly explain something for you. The answer is this. Look at here. The answer to this exercise, it means the spectrum of MF will be the range of f, which is f of 0 and 1. Okay, so it means this is the answer, but you have to show this. You have to prove it, that the spectrum of MF is the range of f. And if you remember, I said this example is a special case of this, right? Why did I say this? Look at here. What happens here in this MF? What happens if f as a continuous function here? Look at here. What happens is fx is equals x. If fx equals x, then if fx equals x, this operator is exactly this operator, right? Because it becomes the multiplication by fx, but fx equals x, right? Okay. So if fx, we have to add here. So let me write if actually. If fx equals x, then this operator that you see here, mf, becomes this operator. It means becomes multiplication by this function, which is x. So here we have fx equals x becomes x times u of x becomes this operation, this operator. And do you remember here the spectrum of this operator was the closed interval 0 and 1, right? Now look at here. The spectrum of the spectrum of that operator was closed interval 0 and 1. But this closed interval 0 and 1, what is it? This is the range of f, right? This is the range of f. Because f here is defined from 0 and 1 to the complex number by this f of x equals x. Now what is the range of f? Is the closed interval 0 and 1, right? So you can see. So you can see that in this example, if fx equals x becomes this, right? Becomes this operator here. And the spectrum of f here, spectrum of m here was, you can see the closed interval 0 and 1. And closed interval 0 and 1 is the range of f, okay? The range of this function. Okay, so the answer is this, but you have to prove it. Okay guys, next we have a very important theorem and interesting. Look at here. Let's say T is a bundle linear operator on a Banach space X. We want to prove that the spectrum of T is a non-empty compact subset of C such that the absolute value or modulus lambda less than equals the norm of T for every lambda in a spectrum. Okay, look at here. This is interesting. It means a spectrum is a compact set, okay, such that we have this inequality. So we will prove the compactness and this inequality, but we will skip the proof of non-emptiness because it's very complicated. So I'm afraid that this is the beyond the level of the class. So we will prove it's compact and this inequality. But before we start the proof, Let me give you a picture about this inequality. What does it mean that for every lambda in a spectrum, the absolute value of lambda less than equals the norm of t? This means in complex plane, which is homeomorphic to two-dimensional space, which is in complex plane, which is homeomorphic to R2, this inequality means the spectrum is contained in the circle centered at origin of radius t. Look at this picture. This means this. It means in complex plane. This is the complex plane which is homeomorphic to R2. The spectrum, you can see a spectrum. This is our spectrum. Is contained in a circle centered at origin of radius the norm of t. This is the picture for this inequality. So bear in mind. You can see here. A spectrum is contained in a circle centered at origin of radius the norm of t. Okay. Now let's start the proof. Okay. Let's start the proof. We want to show this first. Okay, we want to show that for every lambda in a spectrum, the absolute value of lambda is less than equals the norm of t. Okay, suppose the otherwise. Suppose that lambda is an element of a spectrum such that the absolute value of lambda is greater than the norm of t. Then this implies this. This implies the norm of lambda inverse. Lambda inverse, it means 1 divided by lambda is less than 1. Why? It's easy, but actually look at this. When you say the absolute value of lambda is greater than the norm of t, this is equivalent to saying that the norm of t is less than the absolute value of lambda. Now you divide both sides by the absolute value of lambda, of course, because of this inequality, lambda is non-zero. So if we divide both sides by the absolute value of lambda, so we have 1 over the absolute value of lambda times the norm of t is less than 1, and then by the property of the norm, this is equal to the norm of 1 over lambda times t less than 1. And 1 over lambda, it means lambda inverse, the multiplicative, the inverse of lambda, right? Less than 1. Okay, so you can see this implies this. So we have the norm of lambda inverse t is less than 1. Okay, so you can see lambda inverse t is an operator of norm less than 1. So now look at the proposition 3.7. So if you have an operator of norm less than 1, then 1 minus that operator. Okay, look at this proposition. So 1 or I minus lambda inverse t must be invertible. Okay, look at that one. So since this is invertible, if we multiply this invertible operator by some non-zero scalar, let's say lambda itself, so this is invertible lambda times lambda inverse minus I, because look at here, I minus this operator is invertible, so this operator minus I is also invertible actually. Okay, this invertible this is invertible. It implies that this is invertible. Okay, like I minus S is invertible, it is easy to see that S minus I is invertible. Okay, so lambda inverse t minus I is invertible. So if we multiply it by a non-zero scalar, here lambda is non-zero because we suppose this. So lambda times lambda inverse t minus I is also invertible, but this equals t minus lambda I. So when you say t minus lambda I is invertible, what does it mean? It means lambda does not belong to a spectrum. Actually, lambda belongs to the resolvent set. Okay, so since this is invertible, lambda does not belong to a spectrum. So okay, so this is a contradiction, right? This is a contradiction because we suppose that lambda is an element of the spectrum. So this is a contradiction because we suppose that lambda is an element of a spectrum such that this, and we get contradiction. So this shows that, okay, we get contradiction. Lambda does not belong to a spectrum. So it means this is not true. So if lambda belongs to the spectrum, the absolute value of lambda must be less than equals the norm of t. Okay. So we prove this inequality, and this equality shows something, shows something else actually, something else also. Look at here. So we prove this inequality. Then the absolute value of lambda is less than equals the norm of t. This also implies that, look at here, I show you this picture, right? This also implies that the spectrum is a bounded set, right? A spectrum is a bounded set, okay? It shows that the spectrum is also a bounded set. Okay, so far we proved that this inequality is true, and this inequality means the spectrum is also bounded. So to show that a spectrum is compact, it is left only to show that the spectrum is closed. Okay, so we prove this inequality, and this inequality implies that a spectrum is also bounded. So if we show that the spectrum is also closed, so a spectrum is bounded and closed, so it must be compact. Okay, to prove that the spectrum is closed, we define a function like f from complex numbers into b of x by this. F of lambda equals t minus lambda I. So this is an element here for every lambda. We claim that f is continuous. Why? Look at here. Because the norm of f of lambda minus f of mu, this is f of lambda minus f of mu. So t minus t is 0. So left mu I minus lambda I. This is easy to see. And if we factorize I, we have the norm of mu minus lambda I. And look at here, by the property of the norm, this equals the absolute value of mu minus lambda times the norm of I, but the norm of I is 1. So left this. So this shows that f is continuous. Why? Because when mu approaches lambda, f of lambda approaches f of mu. So this shows that actually f is continuous. Okay, f is continuous, right? If you remember from the topology, when we have a continuous function between topological space, then the inverse image of open sets is open, right? If you remember from the how to say from the topology, let me remind you this. So let me remind you this from topology. Okay, f is continuous, right? If you recall this from topology, if we have a continuous function between topological spaces, it means x and y are two topological spaces, and f is a continuous function from x into y. Then when we say f is continuous, it is equivalent to saying that the inverse image of open set here is open here. It means for every open subset like B of Y, f inverse B as a subset of X is open. Okay, this is a very well-known fact from topology. Therefore, look at here, we have this function from this topological space to this topological space. And Bx inverse, do you remember, as a subset of Bx, see this corollary, yeah, 3.8. Bx inverse as a subset of Bx is open, okay, is open. So look at this function from here to here. Bx inverse as a subset of Bx is open, okay. So inverse image of Bx inverse as a subset of C must be open. Now let's see what is this actually. So inverse image f inverse Bx inverse, it means the inverse image of Bx inverse. It means, by the definition, all scalars like lambda such that f of lambda belongs to Bx inverse. And this is equivalent to saying that what is f of lambda is t minus lambda I. When you say belongs to Bx inverse, it means t minus lambda I is invertible. When you say invertible, what does it mean? It means resolvent set, which is the complement of a spectrum. Now look at here, this is open, right? F inverse Bx inverse, which is resolvent set, is open, right? So resolvent set is open, right? Therefore, the spectrum, which is the complement of resolvent set, must be closed, right? Okay. So the spectrum is bonded and closed, so it must be compact. Okay. So you can see we proved that the spectrum is compact set, and this inequality, and the proof of non-emptiness is not required because it's I think it's beyond the level of the class, so we skipped this proof. So bear in mind. Okay, next we have a definition, spectral radius of a bonded linear operator, which is defined to be the supremum of the absolute value of lambda, and lambda belongs to a spectrum. It means the supremum of the absolute value of all elements of the spectrum. And this supremum becomes maximum. Why is it like that? So it should be easy for you to figure out. Of course, because a spectrum is a compact set, right? When you say the supremum, the absolute value of lambda, so since a spectrum is compact, right, this supremum becomes maximum. Actually, this is because look at here, a spectrum is compact, right? So the absolute value is a continuous function. So when we say the absolute value of lambda, okay, you forget about this supremum. The set of absolute value of lambda is also compact, okay, as a subset of R. So it is closed and bonded, especially it's closed. So when you say the supremum of this closed set, and supremum is a limit point, and every closed set contains the limit point. So this supremum becomes a maximum. Okay. Yes. And then what we have. Okay. Let me repeat one more time. Since the spectrum is compact, so the set of the absolute value of lambda is also compact. So is closed. When you say supremum is a limit point. Since this set is closed, it contains every limit point. So it contains the supremum. So that's why supremum becomes maximum. And then look at here, we have this inequality that the spectral radius is less than equals the norm of t. Why is it like that? So it is easy to figure out. Look at here. Do you remember this inequality when we said the absolute value of lambda is less than the norm of t? So it means the norm of t is an upper bound for this set, right? Is an upper bound for this set because the absolute value of lambda for every lambda in a spectrum is less than equals the norm of t. So the norm of t is an upper bound for this set. So when we say supremum, what does it mean? It means the least upper bound. It means it is smaller than any upper bound including the norm of t. But the supremum of this set is the spectral radius. So this is because the norm of t is an upper bound for this set. Okay, and when we say supremum, it means least upper bound. So it must be, and the supremum is this, so it must be less than any upper bound including the norm of t. And then we have a theorem that we mentioned without proof because the proof is very complicated. You just bear in mind the spectral radius formula. We can prove that the limit of, look at here, the limit of the norm of Tn to the power of 1 over n. It means nth square root, right? Okay, so this means actually the nth root. Sorry, I said n square root. Sorry, let me correct it. The limit of the norm of Tn to the power of 1 over n. It means the limit of the nth root of the norm of Tn. Okay, this is easy. When n approaches infinity exists. Okay, this limit exists. and we can show that it is equal to a spectral radius. So actually we can prove that the spectral radius equals the limit of the norm of Tn to the power of 1 over n, which means the limit of the nth root of the norm of Tn. Okay, but the proof is very complicated, so we skip the proof. You just bear in mind. And we have another corollary as another corollary here, yes, that we already talked about. The resolvent set. Okay, the resolvent set. Okay, here should be some typo here. Let me fix this one. Okay, look at here. I said the resolvent set of any operator T belongs to B of X. Okay, this subset of C is a typo, so you delete this. Okay, you delete this. This is typo. Only T belongs to B of X, so this subset of C is typo. You delete this. So let's say T belongs to B of X. Okay, is a bundle linear operator. The resolvent set of T, you remember the row of T, is an open set. Why is it like that? It means the resolvent set row of T as a subset of look at here, it means resolvent set of T as a subset of complex number. This is open. Why is it open? Okay, sorry. Why is it open? Do you remember the resolvent set is the complement of the spectrum, right? A spectrum is closed, so the complement of the spectrum, which is resolvent set, must be open. Actually, we saw this. You remember when we were proving this theorem. Look at here, here, in the proof of theorem 3.14. Here you can see. Look at here. This is the resolvent set is open. Okay, it means in this theorem we've proved that a spectrum is closed, right? Compact actually, so it's bounded and closed. So a spectrum is closed, so the complement of the spectrum, which is resolvent set here, resolvent set must be open.